we're using AI SDK from Vercel to go ahead and create wrappers around these foundational models. My example, we're using OpenAI, and we have a prompt that we're going to feed into the expert. And these provider options down here is how we collect and provide the last response ID of the message from the LLM. We have prompt tokens and completion tokens. You track these so that you can understand what model was used and how many tokens were associated with that call so that you can understand the prices. So whenever you set up your evaluations, you'll be able to see, here's how much GPT 4.1 is costing me. Here's how many, like, on average tokens I get for this specific kind of message. Hey, what's up everybody? Last video, we talked about the difference between workflows and agents, where we said workflows is always a predetermined path of execution where you have multiple LLMs chained together, and it's always step 1, 2, 3. Whereas an agent, I gave my own relative definition and said that I think of it as a system levels architecture that has access to a mixture of different experts, and it has the agency to determine its own path of execution. So the two fundamental experts we talked about is your evaluation expert and your planning expert. So an incoming message comes to the system. The first thing is to evaluate. Do I have enough information to carry out the planning step? If not, ask the user for that clarification. If I do, I'm good. I can move on to the planning phase. So experts here, top level, evaluation and planning. Once it makes it to the planning, that's where it has these different child nodes associated with that state, where it can pass off to different experts that specialize in one thing specific. So what I mean to say is it has access to these three different experts, and the planning expert is the one that will route the task to the most relevant one. Enough of explanation out of the way, let's go ahead and jump into the code itself. Okay, so what we're looking at here is the accountability agent machine. This is the state machine, the heart of the operation, or the brains of the operation, if you will. Over here in my folders, you can see that I have this folder for machines. Right now, I only have this one. I also have experts, which we'll jump into in just a second. And then I also have this file for routing messages to the agent. I call this from an ingest function. An ingest is a workflow engine that allows you to schedule different messages or background tasks for your node servers. If you've come from Ruby and Rails, this is very similar to Sidekick in that you can fan out these different tasks to run in your backend in parallel. So it's really cool. Won't get too much into that just yet, but back over to our machine. So up top, we're importing our necessary APIs from XState, which is what we use to build the machine. Shout out to Stately for providing those. And then we're obviously importing our different experts. So we have our planning expert, and over here we have data aggregators. This is where we're fetching information in certain states. So for example, every time we come into evaluation, we'll go ahead and fetch whatever information we need to make sure that the context is always up to date within the machine. Okay, so looking at the first interface here, this is our plan outline, the timestamp that it was created, and then a collection of steps. So each step contains a status, initial, completed, or skipped, and a unique ID, the name of the step, and step type. It's going to log active workout entry or backfill workout entry or update user preferences. And then you have a goal, top line goal that it's trying to accomplish, and then dependencies. So this is, like I mentioned before, if there's multiple tasks that need to be executed inside of one message that was given to the system, then these are the dependencies where you might see, if we're looking at step 3, the dependency array might include step 2. If we're looking at step 2, the dependency array might include step 1. Okay, so going down, this is for getting the most recent plan. This is just a little helper function because, like we mentioned, there's a timestamp here. So whenever we call this function, always get most recent one. Okay, we have automated transition reasons. So this is to help with the telemetry of looking back at the system logs. Where did it transition from? and we can see, like, for each message that was provided to the system, how the agent started to reason about the different paths. You could imagine this telemetry being super insightful whenever paired with evaluations and what have you, and trying to really study how your machine is working out in production. Okay, so then we have user preferences here. The only things that we care about the system knowing about, or the machine, sorry, is whether or not the user's opted out of SMS messages. This service that I'm building for me and my buddies is primarily SMS based. I will get to more fun UI inside of the web app, but for now, just the MVP is make it such that we can text this thing. Okay, so SMS opted out at, that's nullable, so they may have not opted out, and if they did, then we'd have a date. Preferred name, so this is just like a nickname that you want the accountability agent to refer to you by. Preferred weight unit and distance units, so if we hover over this, you can see it's a enumerated list where it can either be pounds or kilograms. And for distance, we have meters, miles, kilometers. And we're using these types to help inform the system of values that it should be capable of providing. Again, we're adding in some determinism here by giving it guardrails. We're not just saying whatever string you think is necessary. We're giving it specific examples of what it should be choosing from. Okay, so the context. We talked about this last time, that the state machine has context in and of itself. You could think of this as like the state of the state machine at any given point in time. So we have a user ID, a user message that initiated the system. We have user preferences that we grab from the database. We have a conversation ID. So we track in our database for any given day one running conversation ID. If one doesn't exist when they message the system, we create a new one and persist it at that point so that they can continue to message throughout the day and will always reference the same conversation ID. Okay, we have a last response ID. This is super helpful from OpenAI, where you can just provide the last response ID, and OpenAI servers already are taking care of the state for the user interactions with the foundational models. So this is how you can continue to ask questions, follow-up questions in the same conversation at different points of the day. And their LLM will have context of the ongoing conversation that this specific user has had with the machine. So super helpful. Plan outlines. This is just what we talked about above. This is where the state machine knows about all the different plan outlines. But really, for now, we're only ever worried about the most recent one. If we ask the user for clarification on an incoming message, then the state machine will know about it. Next time it's in evaluation, am I waiting for clarification, or did I just get clarification from a user? It helps differentiate certain parts of the prompt that we provide the LLM under the hood. Okay, we talked about what automated transitioning reasoning is. And then here we have today's workout entry and the latest response from the agent. So today's workout entry, whenever we enter evaluation, I mentioned before, we'll always aggregate certain information. This is where we'll populate, has the user logged anything today? So they might be texting one-off messages as they accomplish each set at the gym, or like I like to do, I just wait to the end of the whole gym session and then send it all in one big message. However, the system's smart enough to anticipate both scenarios. They're either going to do it all at once or they're going to do it one by one. So in this way, every time we jump into evaluation, we'll check to see has the user already logged anything for today. All right, so now jumping into the machine itself, that takes care of the types. So let me go ahead and show you. We just went over what the context was. Setup is an API from XState, which is going to allow us to set up the machine that we're about to build and configure. And it allows us to inject these types so that, again, we're type safe all the way throughout the machine. And we know at any given state what structure or what shape of data we should be expecting to work with. Okay, so here we have user submit. This is a discriminated union where what that means is each of these objects have a type associated with them. And this allows us to do very clean pattern matching later on in the code. I'll show you what I mean by that. But the user submit, you'll notice if we look at all of them, if I scan real quick, all of the events are appended with or prepended with agent dot, where the only one prepended with user dot is the message. Okay, so in events is how we transition from one state to the next. What we have here for these events is we have all of these events are prepended with agent dot, which means those are the ones that the system is responsible for emitting. And then the only other one that we see with a user.submit is indeed the only one that is going to be coming from the user. So this is how the user and the agent are talking back and forth to one another. There's only certain states in which the agent will respond to the user, but all of these other events show the agent how to traverse the different paths itself. So because it knows of all these specific finite states that it can be in and how to transition from one to the next, the underlying AI models are very intelligent at picking the most relevant event to submit at any one given point of the state machine's journey. Okay, so there is our events, and then we have these actors which can be invoked. What an actor is just a promise, like a network request. In this example, fetching to the database to get information about today's workout entries. And these actors can be invoked automatically whenever certain stateful transitions take place. So what I mean by that, every time we enter into evaluation, we'll always fetch today's workout entries and fetch the user's latest preferences. And like I mentioned, we could also create these actors. Let me go ahead and pull one up for you. So I'm going to jump into today's workout actor, and this from promise is coming from XState. So up here we have from promise. That's what allows us to wrap this promise that we make to the call that we make to the database in something that XState's state machine can understand. So inside of there, we look at what's the current date. Let's get the start of today and let's get the end of today. So between 12 a.m. and right before 12 a.m. the next day, we'll look for any workout entries that were logged for that day. So this is what that looks like. We're using Drizzle to give our database some types as well. So everything's fully covered in TypeScript. This is such a wonderful place to be in developer experience land, having all of your information typed. It just makes everything so much more straightforward, but also it helps the AI itself. Whenever we're inferring certain types, whenever we use the same Zod schemas and types across our database and inside of our LLM calls, there's so much cohesion in this way. Okay, so as you can see, we're joining a few different tables whenever we search for all the different workout entries. We're checking for strength sets, we're checking for recovery sets, or any cardio sessions that were logged. And of course, we're using the time range to only look for today's entries. Okay, and then we respond with all of that information. All right, so that's what an actor is. Now, back to the point that I was making. I could, in theory, create expert actors for all of my experts that I talked about, but I didn't. So you have the liberty of putting what information you want inside of the state machine, and being selective in this way means that you don't just put everything inside because you can. You only put inside the things that you think make sense. And for me, that's just the data aggregators. This way I can isolate where I make calls to those experts, and that'll be super beneficial in other areas of my application later down the line. Okay, so we covered the setup function from XState to set up the machine. I showed you the different actors that we have access to, and now we're going to create the machine. So context is initialized like so. So we set everything to null. We can set preferred units and distance units to pounds and miles, but that's okay. It'll be updated as soon as we enter the evaluation state and we fetch whatever the user's preferences is. All right, so moving on from the context, we give this machine an ID, an initial state, which is idle, and then here's all the different states. So let me go ahead and collapse all of these so that it's easier to walk through. Almost done. Okay, so we said first is idle, then we transition into evaluate. Evaluate is a compound state where it initially has, so what I mean by compound state is that it's like a parent state with some child states within it, nested within it. That's what a compound state is. So from idle to evaluate, the first state within evaluation is fetching data. We're always fetching data, and whenever we enter that, we're going to do these two things. We're going to grab today's workout entries and then fetch the user's preferences every time we hit evaluation. We always want to do this so that we have the latest up-to-date information. Okay, so inside of fetching today's workout, this is where we're going to invoke the actor that we just went over. This is the input that we're going to provide that actor, so the arguments that we provide the call to make to the database. And then whenever it's done, we're going to target evaluating. We're going to get out of this state and transition to evaluating. If there is an error, we'll go ahead and transition to the failure state inside of the machine. Okay, and assign is just updating the context. We're saying assign the value of what was provided from that output to today's workout entry within the context of the state machine. So this is how it updates its own memory throughout the process of transitioning across these different states. Okay, so fetching user preferences, a very similar thing. We don't have to go over it. All right, so whenever we're inside of evaluating, this is where we talked about before. We can do one of three things. We can ask for clarification, we can start planning, or we can determine that we're complete and there is no more work to be done. All right, so inside of planning, this is where whenever we get an output, we'll go ahead and start to update the plan outline. All right, so pausing there, let's go ahead and take a look at one of these experts. So whenever we go into, whenever we transition to evaluating, we'll be working with this evaluation expert. So we're using AI SDK from Vercel to go ahead and create wrappers around these foundational models. So in my example, we're using OpenAI, and we have a prompt that we're going to feed into the expert, and here we have type information from the machine itself that we're working with, and now we can get into the code of the expert itself. So over here inside of my project directory, I have this file within experts. All right, so let me go ahead and scroll down to the bottom, and then I'll make my way back up to the top. What we're working towards is this right here. This is the call that we make to the model, and this is the specific model that we use. This is the schema that we provided, which is, again, a layer of determinism inside of the system where we're stipulating exactly the shape of the information we expect to get out. So this evaluation expert is going to make a determination for us as to what it needs to do and which state it needs to transition to next. The prompt that we provided is a prompt that we build given the context of the situation, at what point of time and day it's being made, etc. These provider options down here is how we collect and provide the last response ID of the message from the LLM. So this is how, like I mentioned before, we tap into the state that OpenAI holds for us on the back end, which keeps track of the different conversations or the same conversation a user has had. And we just use that in this case within the same day. This is why we pair that last response ID with the conversation ID that we store for today's entries inside of our database. Experimental telemetry is just to understand how many prompts were used inside of the system prompt to go ahead and do something in the LLM, and then how many tokens were used in completion side. So you have prompt tokens and completion tokens. You track these so that you can understand what model was used and how many tokens were associated with that call so that you can understand the prices. So whenever you set up your evaluations, you'll be able to see, here's how much GPT 4.1 is costing me. Here's how many, on average, tokens I get for this specific kind of message. And then you have your evaluations that show you how good you're performing with that system prompt for that message in that scenario. And this is where, at a high level, whenever you zoom out, you can see how much is it costing me and how accurate is this model. and you can start to make trade-offs at different expert levels where you want to mix and match different models. Okay, so then we just respond with the final response of this expert. So what does it respond with? Let's jump up to that. And this is stipulated by the evaluation schema. So this right here, it's going to provide us an action decision, which, as you can see, is an enum, which is stipulated right here. This is where we tell it you can only choose one of these three. Ask for clarification, start planning, or say that you're complete. That's what the action decision is going to be. Then we're going to say, hey, this is the reason why. Notice that I'm putting these describe blocks. This is Zod, by the way, that I'm using to like spell out the structure of the prompt. And all of this information is also helpful for the LLM. It's getting passed to it to describe each field that it should be building out, why that field matters, and why it's relevant to the overall job that's being done. So we have our action decision, which is the next action to take based on an evaluation, the reason for choosing this action, any clarification that was provided. You'll notice that this is nullable, which means you may or may not have to do this. So don't think that it's required for every step of the way. Otherwise, the LLM might get tripped up and hallucinate that it thinks it always needs clarification when really it doesn't. Okay, so that's it. That's the evaluation schema. Whenever we run it, that's the information that we're going to see come out of it. Okay, so from there, there is another one to show you. Now, this is ingest. This is where we actually send a message to the system. And before I actually show what this is, so you could see up here, ingest create function, before we dive into that, let me actually take the time to show you how we use OpenPhone to route incoming text messages in the backend service to the correct system. So in order to do that, like I mentioned, we use OpenPhone. So I have inside of here somewhere I have, let's find it, OpenPhone. Here's a util that we use for sending a message. This is similar to Twilio's APIs. I just like OpenPhone as a new modern alternative. So let's see, OpenPhone. I have a webhook in the backend. So if we go to app and we go to API, here we go, OpenPhone webhook. So inside of here, you could see this is what an OpenPhone message looks like. We have an object with that says it's a message. This is probably OpenPhone's discriminated unions, where object is just the type that they key off of. But anyways, we have from, so who did this come from? Who does it need to go to? The direction, is it incoming or outgoing? The body is the actual contents itself, like the text message. Were there any media attachments? Did the user text over an image? Or do we need to send back an image? Then you have like your different types here. The ones that we're looking for is message received and message delivered. And yeah, so inside of this post, this is just using Next.js on the backend to create a route that our service can always listen for. Whenever we do this and deploy it, we get a URL that we can then give to OpenPhone inside of our admin tools and say, hey, whenever anything hits these events inside of your system, post back that information to my system at this URL. So that's what this webhook backend is doing. It's saying whenever we get a message .received and it has, you know, object.status.received, then we know that we're receiving a message. And this is how we know whenever we're delivering a message, whenever the type is message.delivered and the status is delivered. So then it's pretty simple. We just say, if we're receiving a message, do this, else if we're delivering a message, do this. So whenever we receive the message, we first check, hey, are they a user on the system? If not, send them back onboarding link. So we'll just text them back, oh, sorry, can't help you. Slide over to this URL to create an account, and then we can continue. If the user has opted out, we need to let them know, oh, sorry, you've opted out of text messages. We can't help you, but you can go back here to turn text messaging back on. If it passed all of those checks, we'll then check to see how's the balance associated with the account. You know, as much as I'd love to make something for free, It's not good business practice, right? So even though it is for fun, you never know. It could become something more than just fun for me and my friends. And I wanted to have this already set up so that it wasn't a problem. So for instance, like if any of you watching along wanted to try this out just to see how it is, you could. Okay, so anyways, we'll check to see, do they have a low balance? If so, go hit this link and re-up on your credits. The credits are super cheap. Okay, so if we made it past all those conditions, then this is where we actually we fire a function call to our ingest server, our ingest function. So in here we call it, hey, this is the function that you're gonna hit, which is route message to agent, and this is the data that you're gonna provide it. The incoming message, the user ID, the user's primary phone number, there you go. And then underneath that, we just update the user credits to account for the fact that they've just hit the system officially. So we just decrement by 1 on their balance. Now, with that out of the way, we can actually go through the ingest function and what it does. Okay, so now that we're inside of the ingest function, we already discussed the name of the event, and that's what was fired off back inside of our OpenPhone webhook. And inside of here, now we're going to get whatever the existing conversation is. In case they already started a conversation earlier in the day, we're going to grab the conversation ID so that we can also pluck out the last response ID and then update our state machine to understand all of these things. And that way, each expert inside of the machine also has that last response ID that it can latch onto to pull from OpenAI the state of that conversation that it's had earlier that day. Okay, so this is what that is. Inside of ingest, you could just say hit this step.run. Each of these step.runs is its own Vercel function. So now Vercel has really generous limits on how long functions can run. I think it's like 14 minutes, which is more than enough for what I need these systems to do anyways. Okay, so get existing conversation. So this is what it's going to do. Go through and get the existing conversation and return that inside of here. Then the machine, we're going to actually invoke. So that's its own step. You have spawn accountability agent. That's the machine that's going to run. Inside of here, we create an actor with the accountability agent that we get from the machine itself. So back over here. So now we're saying, hey, take this machine and create an actor that we can communicate with. So inside here, we set up a bunch of initialization logic. We default everything to null. And then as we make our way through the machine, we'll update this information. So we subscribe to the accountability agent, and then we pattern match off of its state. So for this pattern matching, I'm using TS pattern, which is really helpful. Definitely recommend checking this out. Again, whenever you have everything typed, you can see TS pattern, just building off of the name. Whenever we have everything typed, it makes it so straightforward to reason about the logic. Okay, so going back down. So we've subscribed to the accountability agent. Whenever it's in idle state, we'll just log that it's in idle. Whenever it's complete, do this. Whenever it needs to handle service questions, do this. If it's in clarifying, yada, yada, you get the point. So I'm just going to collapse all of them so that we can reason about it more easily. Okay, so now we're looking at the accountability agent itself, or I'm sorry, where we subscribe to the agent. This is how our server is listening for whenever it finds itself in these states, what it should be doing. So whenever it goes to evaluating, inside of here, we'll just log that we've transitioned into the evaluation state. Here's where we grab the most recent plan outline, and then we check to see if there's any steps within that outline. The last response ID, we're pulling off context from the state machine itself. Then from here, we're checking, should we check the last step to see if, so we'll always check last step where we have more than one step. And whenever we do this, we're just checking to see, like, is the plan outline complete? Like, was the last step within the plan outline marked as skipped or completed? If so, we're done. Send to the accountability agent machine that we're complete and say the reason is that all steps have been planned, or sorry, all steps in the plan have been processed. And again, we pass over the latest response ID always. All right, if we're not there, then this is the first time that we're hitting the evaluation expert, or perhaps another turn before we're ready to mark everything complete. So in any case, we pass along the state context over to the expert. The expert then makes use of the context that it needs. So it grabs the latest plan outline. It also looks at the previous plan outlines and sort of like splits those apart so that it can hand both to the system. It grabs today's workout context. So this is where we take in the workout information. We have structured information that we then parse and then create a part of the system prompt with. So you could see like I'm pushing new lines into my prompt based off the information that I have available inside of the workout that I've just collected from the database. Okay, and then we use TS pattern again to match on the evaluation output. And we can do that because, as we showed before, we have a discriminated union for the action decision. So inside of this object, what comes back is going to be this information. So going back over here, we'll pattern match on part of the object from the evaluation expert, and we're looking at the action decisions. Where we determine we need to ask for clarification, well, we know what we need to send back to the machine, and we know what information to pass back with it. Same here, if we need to start planning, we do this. If we've marked everything as complete, we do this. Okay, so you can see how we use these systems to inform the machine itself, how to continue to transition. All right, so inside of planning, if we go over here, we'll check here what the plan expert does. Again, same thing, we're passing along the context of the state. So if we go look at the planning expert, up at the top, you'll see here, you can log today's workout, you can backfill a workout entry, you can you can update user preferences. For example, I might text it and say, hey, can you update my name to Boutte instead of calling me Victor? You can see the different available step types. And this is where it will build out the plan schema. So we talked about this earlier whenever we were looking at the different types. This is just the Zod version of that, where I'm also adding in these describe blocks, which are helpful for the LLM invocation. So then if you go down here to the actual invocation, we're generating an object from an OpenAI model. That model is 4.1. We pass along the planning schema, the planning prompt, and you get it, the same stuff that we just covered before. So back over here, whenever we listen for the output of that, then again, we know, should we be backfilling the workout entry? So we send the agent into the correct state. So now that we've covered those experts, we've covered a little bit of the code. What's the state machine look like? What does these ingest calls look like? What does the context we're passing around look like? You sort of understand how the system all comes together at this point. So if I go back and minimize all these different states that we're pattern matching on, just to recap, we said that we created an actor with the state machine, which we can communicate with, and then we subscribe to that agent so that we can pattern match off of which state it's in at any given time. And whenever we've traversed through all of these and the system has determined that it's complete, this is where we'll hit this block, and we'll, inside here, there's this console log to say we've transitioned to complete. And this is where we send back the final message to the user. We give them the response from the agent. And at that point, they know that everything is complete. Okay, so that's it. Really hope you found that helpful. I'll put out another explainer video and then another tech dive after that. But yeah, thanks again for following along.